this. Okay, that's happening. All right, thanks everyone for joining. This is the second of 6 of these town hall sessions, although each of there will be 2 sessions. So this is the first of 2 for this survey. This is our session on the definition of the high latitude time domain survey, and Brad Cenko is here to present. I'm here. I'm Tom Barkley. I'm here from the Roman Project Science Office. We've also got folks attending from both the 2 science centers, the Science Center at IPAC and the Science Center at Space Telescope Science Institute. So they're on hand to potentially answer questions. The idea is this is an interactive session with lots of questions. This is your opportunity to talk to and get feedback from the people who are defining these surveys. So please try and make use of this time. I'll mention it again at the end, but there will be a link to a Q&A or a form to fill in so you can kind of ask questions, and they'll get to us, and we'll make sure that kind of feedback is responded to. So without further ado, I think we can start the session with Brad. So take it away.
All right, thank you, Tom. Hello, everyone. Let me share my slides here. All right, hopefully you can see those, and they are in full screen mode. My name is Brad Cenko. I'm at NASA's Goddard Space Flight Center. On behalf of myself, my co-chair Masao Sako, and the broader team of folks who make up the High Latitude Time Domain Survey Committee, we're really happy to present the work that we have been doing so far and to hear feedback from all of you on the direction that you think we're going in for this. So this is photos of all the folks who have been involved in this committee. I have to say it is been an extremely enjoyable experience to work with all of these folks. This is hard work. It's things that, is on top of all of our responsibilities, and it's, done in service to the community to try to define the, best survey for Roman. But it's been really fun working with all of these people. I need to particularly acknowledge the really good support we've gotten from the project infrastructure team for Supernova, who have provided a bunch of the simulation results and figures that I'm going to show throughout the bulk of this talk. But I saw that there were a number of folks from the committee there. So if you see them, please thank them for all of the hard work that they have been doing to make this, a really powerful community survey for all of you. Taking a step back for the moment, just to make sure we're all on the same page here, need to remind everyone of the main observational program that Roman is going to conduct over its 5-year prime mission lifetime. There are 3 large core community surveys that will take up the majority of this 5-year prime mission lifetime. One of those, the Galactic Bulge Time Domain Survey, is dedicated to finding an unbiased census of exoplanets through the microlensing technique. And not surprisingly, that will be looking in the galactic bulge. 2 of them will be primarily extragalactic surveys. The High Latitude Wide Area Survey, which is designed to enable weak lensing, BAO observations, primarily driven by cosmological requirements. And the one that I'm going to talk about today, the High Latitude Time Domain Survey, which was designed to find high redshift type 1a supernova, use these as probes of the cosmology of our universe. That's what we're going to hear about over the course of the next 2 weeks from the committees that are working on this, but it's also important to keep in mind that that's just a fraction of what Roman will be doing. At least 25% of the time will be available to the community through a galactic plane survey, as well as a general investigator program where people can propose for additional surveys with Roman. So I just wanted to make sure, we understood that the context here, but today I'm going to be focusing almost exclusively on the high latitude time domain survey. The job of our committee, if you'll forgive the Federal Reserve references here, is kind of twofold. We have to make sure that we recommend a survey that can meet the mission, high level science requirements that are all related to type 1a supernova cosmology. It was one of the main goals of the mission, one of the main reasons it was recommended by previous decadal surveys and implemented by NASA. So we need to make sure that at the bare minimum, we're recommending a survey that achieves those goals. But at the same time, we also want to recommend a survey that maximizes the broader scientific return for the entire Roman community. So I'm going to refer to this throughout this talk as, community science. It's not to say that type 1a supernova cosmology is not community science. All the Roman data is public. The community will certainly have an opportunity to engage in that science as well. But there's a lot of additional exciting science that can be done with a high latitude wide area, a high latitude time domain survey. And so that's the other thing that our committee has started to think about, that previous working groups that have been looking at the high latitude time domain survey haven't really been working on. So we really are supposed to be, your voice, the community's voice to the Roman project. And we have, throughout this process, undertaken a number of opportunities to get feedback from all of you. And so this is another great opportunity to do that today. So the first thing that we did when getting our committee together was try to make sure that we understood what were the detailed requirements related to supernova 1a cosmology. And just as a kind of brief refresher here, right on the right-hand side of this plot, you can see the scale factor of the universe as a function of cosmic time. And if you look back at higher redshifts, the universe is decelerating due to the presence of dark matter. Several decades ago, it was realized that the universe experienced more recently an acceleration area that has been attributed to dark energy. Supernova are very powerful probes of the scale factor, type 1a supernova in particular, because they are standardizable. They're not perfect standard candles, but they obey a pretty good relationship or a number of relationships between their light curves, the width of the light curve, the color of the supernova, and the luminosity, the peak luminosity and the corresponding luminosity distance associated with those sources. So if you look on the left, you can see kind of the state of the art, a Hubble diagram here showing what's been done. This is from the Dark Energy Survey collaboration that has found a large number of type 1a supernova in what I would call kind of an intermediate redshift range, redshifts of order of 0.5, combined with a nearby sample from other supernova surveys. You can see that you can make powerful progress to constrain fundamental cosmological parameters of our universe by using these standardizable candles. The way that this is quantified in the science requirements through Roman is in terms of what we're going to refer to throughout this talk as this Dark Energy Task Force Figure of Merit, or FOM. This is essentially a simplified way of thinking about this for most systems, as this is the area in phase space of the W0 and WA parameters, cosmological parameters that describe the equation of state of the universe, that is, effectively inversely proportional to the area of this error ellipse. And so the larger that this number is, the more precisely we are able to constrain these two fundamental cosmological parameters that sort of characterize the properties of dark energy, we think, that we don't understand very well. And the number here that was chosen, 325, this was chosen specifically to represent, more or less an order of magnitude improvement over, current state of the art facilities that were up there when and operating when the sort of Roman requirements were written. So this figure of merit number is what we're going to come back to, like I said, sort of throughout the bulk of this talk. But just keep in the back of your mind, it's effectively just a metric that's defining how precisely we can constrain these fundamental cosmological parameters. So in order to do that, using type 1a supernova, there are a number of requirements that kind of flow down from that, or implementation choices that flow down from that. And those describe the supernova, sort of redshift range over which we want to actually measure these supernova in order to measure the scale factor as a function of cosmic time. We need to have supernova over a relatively broad range of redshifts. The numbers that are in the requirements documents are ranging from a redshift all the way down to 0.2, relative nearby universe, up to a redshift of 1.7, where we have very few type 1a supernova known at the moment. And there are requirements that say, how many supernova we need in each of these redshift bins, things about the systematic bias in redshift for these measurements. But probably the most relevant ones and the things that we've spent, sort of more time thinking about is where and how to place observing fields in order to discover the appropriate number of supernova. And so there's a series of requirements that describe, we want to observe fields that are at low galactic latitude and low ecliptic latitude so that we maximize the sensitivity to the supernova themselves and find these to the highest distances and largest redshifts that we can. We want to have really nice light curves because this standardization process that I described earlier to turn these into accurate and precise, distance indicators, we actually need to measure the light curves of these sources, and we need to do it over multiple photometric bands. And so there's a requirement that, Roman can enable a continuous viewing zone over a sufficiently large area that's suitable for observing supernova. It needs to enable a supernova survey that can monitor these fields with a reasonable cadence. And that's something, returning to these fields on a given time scale. That's another thing that we've spent a lot of time thinking about. And the requirement is that the observatory and everything associated with it needs to enable a supernova survey that can return with a sampling cadence that's less than or equal to 5 days. And as I said, we need light curves in multiple bands. And so the bandpass that we're talking about is at least 6 filters operating over this from 0.5 to 2.0 microns. So those are the high level supernova 1a requirements that we need to make sure we design a survey that meets. The next thing that we did was we looked at the work that other groups had done to demonstrate that there is a survey design that will meet these requirements. And so the Roman project over the previous 5 to even longer than that, I think even decade, has funded a group of scientists to look into this and to design a reference mission for the high latitude time domain survey. This reference mission, again, is not, globally optimized over all the different science that we want to do, but it was really designed to demonstrate that there is a survey that can meet the, supernova 1a cosmology requirements that Roman has. So this is kind of, outlined very nicely in this paper from 2021 by Ben Rose. The basic idea is that this survey would take up 6 months of observations over a 2-year period, nominally the middle 2 years of this 5-year mission. So you have a year and a half of other surveys going on. In the middle 2 years of this 5-year mission, every 5 days or so, you're coming back to these same supernova fields, observing them, getting light curves for them, doing that for a period of 2 years, and then doing other surveys for the remainder, the 1.5 years of the mission. What this plot on the bottom shows very nicely is that in order to get continuous light curves and be in the continuous viewing zone for the observatory, that definitely constrains the locations on the sky where that survey can be conducted. And specifically, it needs to be done at ecliptic latitudes that are either larger than 54 degrees or lower than negative 54 degrees. So the survey needs to happen, either at high ecliptic latitudes and or at low ecliptic latitudes. And the other thing you can see here, the galactic plane, which is shown as these kind of yellow dots here. The foreground extinction is the color bar. You can see the scale over here on the right. And again, we want to avoid areas of large foreground extinctions so that we have the most sensitivity to the supernova itself. So the specifics of the reference mission, it was 30-hour visits every 5 days for 2 years. That works out to that 6 months of observing time over a 2-year period. It was divided up into imaging, which was 75% in the sort of nominal reference survey that they put forward, and spectroscopy, prism spectroscopy, that took up 25% of the total time. And it was also divided up into 2 tiers. So there was a wider tier that had an area of 19 square degrees. This was designed to target lower redshift, where lower redshift here means something like a redshift of 1, type 1a supernova, and a deeper tier that was designed, something like 4 square degrees, redder filters, designed to target the more high redshift supernova to fill out this redshift space. Okay, so that is the reference mission in a nutshell. After that, after we familiarized ourselves with the work that was been done in the past, we started to look at the broader range of community science that could be done with a survey like this. The way that we did that was looking at the activities that were community activities that were organized by the Roman Project. We received a large number of white paper pitches, white papers, and white paper updates. You can see sort of a word cloud of the topics that were covered by these. Again, a broad range of things from galaxies and static science to the full range of transients that are out there, to even solar system science in our solar system. We made a presentation and a status update in July of 2024 at the Roman meeting at IPAC, and held public working group meetings face-to-face and online while that meeting was happening. We gave a presentation to the STRIDE working group. STRIDE is the community time domain working group that is supporting the Roman Project, to make sure that people knew what we were working on and to get input and feedback just a few weeks ago. And of course, we're doing this community forum update today. Okay, so having done that, we sort of divided ourselves into 5 different working groups, where we thought these were, reasonably separable topics that people could narrow in and focus on and do some trade studies to figure out, what is the sort of optimal set of recommendations that we want to make to meet this dual mandate that we have. And the 5 areas that we sort of divided up into, one was, we're calling it cadence, filters, depth area. This was, the trade space in the sort of details of the survey design to meet this dual mandate to do the supernova cosmology and enable the broad range of community science. The second one was to look at the fraction of time that should be devoted to spectroscopy. This was somewhat of an open question from the reference survey. There was a broad range of opinions, I think, in the type 1a supernova community over how much time should be devoted to prism spectroscopy. And so that's something we wanted to understand both from the type 1a supernova perspective and from the broader community science perspective. We had a group of people who were looking at field selection, where the fields should be specifically on the sky, thinking about things like visibility, complementary data sets, and and those types of issues. We had a group of people thinking about survey extensions, right? The reference mission was solely confined to a 2-year period in the middle of the mission, but you can imagine there are long time scale things over which you might want to conduct observations over different time scales. You might want reference images earlier in the survey. You might want different filters than the type 1a supernova science is thinking about. So those are the types of things that the survey extension group was thinking about. And we have a group of people thinking about leveraging complementary data sets. And in particular, there's been a lot of emphasis thinking about the Roman supported Subaru time that's available. So I'll walk through sort of where all of these stands, what we have what we have concluded at the moment, what we think is still open, and then provide an opportunity for you all to provide feedback on all of these things. In terms of the cadence, filters, depth, area, details of the survey design, the overarching approach that we've tried to take is to identify a range of survey designs that meet the supernova 1A cosmology requirements. And then once we have met that sort of baseline or floor, prioritized amongst those that enable the broadest range of community science. In looking at all of the science that we heard about from all of you in the white papers and the feedback we've received, one thing that has definitely struck us is that it's extremely broad in nature, and it's really hard to say, oh, there's one, specific community science goal that is way more important than everything else. And so we're trying to enable a survey that, really enables the broadest range possible of community science. And so we want to start with defining really the acceptable range of cadence, and then work towards the question of which filters, the depth, and the area. And in my mind, at least, in thinking about time domain surveys and how to put those together, the cadence is always the thing that really most strongly constrains the range of science possible. If you have some group of sources you're interested in, you can always make up for a small area by going deeper. You can always make up for certain filters by, changing your area or changing your depth. But if you're interested in things that are on a short or long time scale and you aren't probing those time scales, there's really nothing you can do about it. And that's why I tend to think, about cadence first. And the complication that we have run into and are still kind of sorting out when thinking about these issues is that the figure of merit number that you derive depends pretty sensitively on what you assume about complementary lower redshift type 1a supernova that are out there. The general assumption is that there will be a nearby redshift less than 0.1 sample that's going to anchor the Hubble diagram in the relatively local universe. But a project like Rubin, and the question is, do you assume that there will be a Rubin sample at intermediate redshift to complement the Roman sample and inform the design of what the Roman high latitude time domain survey is going to look like? Now, Rubin exists, it's there, it's going to conduct a supernova survey, and I think it's pretty reasonable to assume that it will be successful in doing so. But the challenge is that the Rubin sample is not necessarily going to be available to the entire Roman community. And so on the one hand, we don't want to design a survey that's going to replicate what Rubin is going to do. But on the other hand, we also don't want to design a survey that only certain members of the Rubin community that have access to all of the Rubin data products can take advantage of, whereas other members of the Rubin community, who don't have, other members of the Roman community who don't have that access can't take advantage of it. And this really does drive the, survey to some extent. If you don't assume that there is a population of intermediate redshift supernova out there, then you're really pushed towards covering larger areas with Roman. You're pushed towards observing an R band to discover a sufficient number of events at a redshift range, in the redshift range of around 0.3 or 0.5. And so the approach that we've settled on here is, there's definitely a unanimous feeling amongst the committee members that Roman should be focusing on the unique science that Roman can conduct. And that really is at the highest redshifts at the near infrared wavelengths. We've started working with the Roman project to attempt to negotiate a public release of relevant Rubin data sets that would allow the sample of intermediate redshift supernova to be available to the entire Roman community. And we're going to probably, since that's going to take time, we're probably going to have to end up recommending distinct surveys depending on Rubin data availability. But I think our preference will be pretty clear, again, in having Roman focus on the things that it can uniquely do well. And this is just showing, the difference in the figure of merit. The blue and the orange points down here are if you just incorporate Roman data, where if you include the Rubin data and tweak your survey design slightly, you can see that you're talking about very large changes in the figure of merit associated with this. So this is a pretty important consideration. Okay, the cadence results, the supernova 1A cosmology requires cadences ranging from 5 to 15 days. You can see that on the left here. This is a plot showing the figure of merit is the color bar here as a function of the cadence for a wider tier and for a deeper tier. Shorter cadences, which correspond necessarily to smaller areas on the sky, really have no benefit for the cosmology analysis. Longer cadences, once you get longer than 15 days, you sort of lose the ability to match the supernova 1A templates and to really to standardize the supernova. And so one of the things that I think we've concluded is that it's really not possible within this survey to accommodate the highest cadence, transients and variables that people have expressed interest in. That's unfortunate, but we have to make choices associated with the survey. There is the opportunity to augment the high latitude time domain survey with guest or general investigator programs. But the shortest timescale stuff, we just really can't design a great type 1A supernova survey and do that at the same time. One of the things we are looking into at the moment is considering variation instead of a purely fixed cadence of 5 days or 10 days or whatever, but allowing for that to vary over the 2-year period to avoid aliasing for periodic sources and to fill out AGN structure functions. So that's something we're still sort of digging into at the moment. The filter depth area trade space is something that we're really sort of actively pursuing at the moment. The preliminary results, largely driven by the simulations that the Supernova Project infrastructure team has put together, are that, this sort of wide and deep tier seems like the best approach. There doesn't seem to be an extremely strong advantage to adding a medium tier. It seems like we need at least 4 bands in each tier for photometric redshifts, for template matching, for the type 1A supernova. But we don't necessarily need all of those 4 bands to be observed in every epoch. And so interlacing the filters, where we observe a couple of filters in epoch 1, different filters in epoch 2, seems like it's providing sufficient temporal coverage, but also allows us to increase the survey area to find lots more of the different types of transient and variable sources that all of you are interested in. But that's something we're still refining. We're improving the simulations. We're narrowing in on the range of things that we think are possible. And that's something we're going to be focusing on over the coming months. In terms of the spectroscopy fraction, one of the things that we've learned is that the prism spectra, while they do have some benefit, for example, for things like twinning, that benefit is not extremely large, and it dies off relatively quickly as you look at larger and larger fractions of time spent on spectroscopy. So you can see here, this is one particular realization simulation showing the figure merit as a function of the spectroscopy time. That falls off pretty rapidly as you get to larger numbers. And so, likely the prism fraction of the survey is going to be less than or of order 20%. At the same time, there are lots of other reasons besides supernova cosmology that spectra are useful and exciting. Classification, training, something that's highly unique to Roman. There aren't, other spectroscopic time domain surveys, or very many of them out there, particularly at these wavelengths and sensitivity. And so we're exploring a range of spectroscopy fractions that are in the, 10% to 30%. To sort of fine tune what specifically that number would be, but I expect it will settle somewhere in that kind of range. In terms of field selection, we found strong motivations for splitting the survey fields into two distinct areas, one in the northern and one in the southern hemisphere. This provides for cross-validation or testing of the cosmology results. Given where the ecliptic poles are, these are necessarily going to be separated in right ascension, and so there would always be one particular area on the sky where you can do concurrent ground-based follow-up of a Rubin high latitude time domain survey field. And there are really strong complementary data sets, both in the south with Rubin and in the north with the Subaru time that is available, that motivates that. For the specific fields, it's something we're still looking at a little bit. In the south, the Euclid deep field seems like a really compelling choice, in particular because Rubin has decided that this will be one of its deep drilling fields. And so having the broad multi-wavelength data, having the concurrent Rubin data, and the Roman data, we think would make for a really compelling and exciting data set. In the north, we're currently leaning towards Elias N1, although I would say others are still in consideration, and we're trying to do some more simulations about things like foreground extinction and looking a little more at what multi-wavelength data sets are out there. The other thing that we're still thinking about and trying to simulate is how to apportion the wide and the deep tiers in these two different fields. It's not necessarily the case that half the wide area and half the deep area would be in the north and in the south. There may be good reasons why you would want one in the north or one in the south. That will definitely depend somewhat on the allocation of Subaru time, but it's something we're still trying to sort out at the moment. Survey extensions, we think there is really compelling motivation. A lot of this came from the great white papers that many of you wrote for extending the survey beyond the nominal 2 years and beyond the nominal wavelength range over which the Type 1a cosmology supernova survey was originally defined. One of these is, kind of obvious, is having reference images obtained prior to the beginning of the survey is really necessary to enable real-time science. If we don't have the templates available, you have to build those up over the first weeks and months of the survey. You lose the kind of real-time component over that 2-year period, whereas if you do that beforehand, you have those in hand. You could also come up with a way, we think, of collecting this that allows you to test the pipelines early on and make sure that all of your infrastructure is in place so that 2-year period where the main survey is running, you're really sort of hitting the ground full steam. The other big extension that we've been thinking about is expanding the temporal baseline. Roman is uniquely capable of discovering high redshift transients. Necessarily, these have longer time scales. Tidal disruption events, pair instability supernova, AGN, all of these would benefit a lot from extending beyond the 2 years. And the last thing that we've talked about is the potential of doing K-band observations. This is not in the supernova survey. It is not the K-band is not as well characterized as the other filters, and it is somewhat less sensitive than the other filters. On the other hand, it does open up a unique wavelength space, and so we're looking at the potential for doing that. The thing that we're trying to decide, when we hone in on all of our recommendations, Should this be in our in-guide request? Should this be in our under-guide request? Should this be in our over-guide request? What that means is, we've been given 3 different time allocations by the Roman project that we should work towards: an in-guide, which is our nominal request; an over-guide, if there's extra time available, how would we use it; and an under-guide, if for some reason there's less time available than is currently understood, what's the sort of minimum available that we could work with. And so deciding, where all of these fit into all of that is going to depend on the results of the survey analysis. So we're kind of waiting on that to have those discussions. Leveraging complementary data sets, 100 nights of Subaru time have been reserved for joint Roman science for the high latitude time domain survey. These could be critical for host galaxy spectroscopy, transient classification, concurrent imaging. We are currently trying to understand the constraints that are out there, when the PFS, the multi-object spectrograph, is available, how much overall demand is there, how much time could we reasonably expect, to inform things like the field selection and the details of the survey. Okay, so that's sort of the work that, a status update of where our work is. This is kind of the calendar. We are now, in the sort of August, September frame, what remains to be done: refining the trade studies, simulations, developing detailed implementation plans. We're going to try to present, a more fleshed out version before we make our final recommendations in November, to have another opportunity for feedback. But ultimately, we need to deliver a report to the Roman project in November, and that's kind of the end date of this committee. So with that, I will wrap up. I'm happy to have discussion, questions. I'm going to put up here the QR code. It's a questionnaire. If you have questions, if you have input, please fill out this questionnaire. Please feel free to reach out to Masao, myself, any of the other members of the committee. We want your input. We want to make sure that we're designing a survey that will do as much community science as possible. And so thank you all very much for attending, and happy to take any questions.
Thanks, Brad. So we have plenty of time now for Q&A for Brad on what's been presented. This is your kind of opportunity to provide feedback and clarifications. Okay, there's a question in the chat. I can read it out. It's what are the Rubin data products which are only available to a fraction of the community and are concerning for your committee survey design? The context: the Rubin alerts are public for everyone, and there will be data releases.
Yeah, good question. The things that we're thinking about are largely, cosmology related data products. And so, for those, you need light curves, final calibrated light curves for a large number of supernova at intermediate redshift. It is true that there will be alerts that are public to the world immediately. It is true that there will be data releases, but those are not public to the world, as I understand it. Those are limited to United States, Chile, for example, and the Roman community is broader than that. And so the things that we're thinking about are, if you want to do a cosmology analysis and you're part of the Roman community but not in the US, do you have access to these light curves for the intermediate redshift supernova to do that? And as I understand it at the moment, the answer to that, might be no. So those are the kinds of things that we're thinking about. Can we make sure that those are available to everyone? and then, modify our survey design accordingly. Does that answer your question, Igor?
Yeah, sounds like it was answered. There's a hand up from Sarab.
Brad, thanks a lot for this. Maybe just to follow up on that, the data releases do become world public after some amount of time after they are released. I don't know exactly that number. So it's possible that your committee could say, well, we're going to look at 2 years in the past data release and use that as the sample that would be available at the same time as Roman. But I don't know exactly what that number, if it's 1 year or 2 years. Could you show that slide that you had of the cadence versus figure of merit?
Sure. Let's see here. Can you see it? Is this the one you wanted?
Yes.
Let me bring it up larger for you. There you go.
So it looks like the figure of merit improves substantially as you go to the upper right.
Yep.
And so that's longer cadence for both. I presume that's coming from just you can just do more area, that's mostly what's driving it.
Yep.
So I worry a little bit about this, where if it's only statistical uncertainties, when you have very sparsely sampled supernova light curves, it can look great if your templates match perfectly, and then you just get a lot more of them. But there is this other part that really would cut off that upper right part, where you're just like, actually, I don't even know what kind of supernova that is, or all these other things. And so just a little caution in using a plot like this, which seems like it's driving you to the upper right to very long cadences and wide area.
Absolutely. I think, when looking at this, two things. So first of all, you're totally right. Second, we are going to redo the simulations with more systematic uncertainties included in them. What we wanted to do was come up with some simulations that narrowed down the range of things that we wanted to run, because those are more computationally intensive. And when I say we, I mean the Supernova Project Infrastructure team, not necessarily our committee. And the second thing is, we're really not considering, cadences, longer than 10 or 15 days, even if on this you would say, oh, keep going, right? 20 days, 30 days, whatever, who cares? For the exact reasons that you say, because there are things that limit you, that, aren't necessarily captured by this. So it's I think in the range of 5, 15 at the longest, probably more like 10, is where things are gonna settle.
Thanks.
All right, no other questions coming up now.
There's a question in the chat.
Thanks, Ari. Do we know when the 2-year survey will happen, in the sense, will it be the beginning of the Roman mission or towards the end?
So the reference design missions, which again are not necessarily exactly what's going to happen, but I think are a good, starting place at least. The 2 years of the high latitude time domain survey were exactly in the middle of the 5-year prime mission lifetime. So no supernova stuff for the first year and a half, 2 years of the supernova survey, high latitude time domain survey, sorry, and then no high latitude time domain survey for the last 1.5 years. I think, certainly not certainly. I suspect that that's where it will end up. And so if you assume a launch date at the end of 2026 and some checkout period, then I would guess the high latitude time domain survey will start sometime in 2028, end of 2028, something like that. But that's something, that's a hard thing to say, because there's a committee that sits on top of us that takes all our recommendations and tries to figure out, can we actually execute what all these individual surveys recommended together in one mission? And so that, I can't promise you that that's exactly how it's going to end up, but I suspect it will be something like that.
Yeah, I can just add to that of what happens next. So these committees write their reports, which are due in November. They go to this high-level committee, which we're calling the ROTAC, the Roman Observations Time Allocation Committee, which synthesizes the report and, very importantly, has representation and a remit to consider the Roman General Astrophysics Survey community, and that they're the ones who will design the work out how the various surveys work together. That said, I think it's highly likely that what Brad discusses is the workable solution, simply because the galactic bulge time domain survey has really wants their data at the beginning and the end of the mission, and so that naturally puts this survey, which also needs kind of continuous time, in the middle of the mission.
And as I said, I think there's a strong case for doing extensions to cover the longer temporal baselines for the high latitude time domain survey. But, realistically, what that's going to mean is it's not going to be, an every 5-day cadence kind of thing. It's going to be, well, can we get images of these fields every month or two, around the bulge sort of observing campaigns. I think that's kind of what we're looking at. And then that hopefully will let you capture the long time scale things when you can get the shorter time scale things in that 2-year window in the middle.
A question from Ari.
Uh-oh.
Hey, Brad, great talk. So I'm gonna ask this question with my science hat on, not my functional hat. I was hoping you could speak a little bit more about the K-band analysis that your team may have been doing. I'm curious, if the K-band could potentially be more advantageous to that survey, if certain things were, I don't know, better characterized or calibrated. I don't know what the limitations are for that. I do personally think K-band is a great resource, and I'm just wondering if there is the potential to use it, and if so, what would have to be done to make that usable? And if it's not usable at all, that would also be good to know.
Okay, let me frame this by saying I think this is something we're still discussing. So take this as not, the view of the entire committee, but take this as my personal perspective for the moment. Okay. The two things that make the K-band really hard for the main, high latitude time domain survey are the less, as I said, sort of degree of calibration and characterization, which, as you mentioned, maybe this is something you could get around. And because of the higher background, the sensitivity is significantly reduced. So unless you are looking at things that are extremely red, you are much better off in going slightly deeper in the H band or whatever the next Redis filter is than, how deep you can go in a fixed amount of time in the K band. So given all of those things, certainly the recommendation from the type 1a supernova people is no K band. Will that outweigh some of the other reasons you might want it? Because it's, if you want a really high redshift thing, there's no flux in the H band and K band's the only option. I don't know. But those are the kinds of things that we're thinking about.
I don't see any more questions right now, so I will use this time to remind people to fill in the form. Ari posted it in the chat, and Brad had it in his slides, and Ari can probably post again so people can have it at the visible. we'll have more of these sessions. There's a High Latitude wide area survey one this week, and then there's 3 more next week. These will be recorded and made available on our Roma forum site, so you can access these. And a reminder, so we also run a series called the Roman Community Forum, which is enables us to provide updates on how the mission's going. And we'll have one of these this afternoon at 4 p.m. Eastern. This week we're focusing on the latest results from all the Roman testing. So this is a fairly deep dive session looking at real data that's come off the Roman cameras and sensors, discussing what data we have and highlighting ways that you can become involved in working with this data through the calibration working group. So probably last call for questions. Discussion. All right, I don't see anything else, so I think we can call this. Thanks a lot, Brad, and thanks for the great questions from everyone, and we'll see you again soon.
Thank you all.